This is probably the hardest for us to teach because prayer blocked by his other day. I am kidding you, Prayer. Man. So this will be hard for both you and me. So I'm going to try and keep it to the bare minimum. And to begin with, this was supposed to be Saturday like at 3 in the morning, but I test, then you can't really control everything. So this did not offer lecture. Earlier, part. But yeah, so I start with the picture. Of course, everyone knows who this is. This is BRAC in its old age. The great physicist. Now, the word goes that when BRAC came up with the equation, he was so impressed by it. BRAC was one of the first physicists who promoted this notion of beauty equation, right? So the elegance of math that comes out of physics. BRAC was one of the proponents. And when he wrote down his equation, when you have aggregate equation, he thought to himself, and actually conveyed it to others as well, that my equation is more elegant than I. But if you look at pictures of the underversion of the rock, he looked pretty elegant himself. Anyway, but humble guy likes his equation perfect. So this is his equation, the rocket case. And then you look at it, you actually kind of stop and marvel at it a little bit because looks so simple. It had just Dhaka, this nice looking contractions, and on the right hand side it's 0. So this is overall what you will call a perfect equation. But hidden in this small thing is a big information about nature, and that information is how you describe articles that we're made of, how we describe matter. And matter is mostly permeable. So this equation turned out to be crucial for life that we know. So why you read it, that I just said, it describes objects called fermions, and if you're a little bit more technical, it's basically describing what we call spinor field. So far, we have talked about fields a lot. We have covered scalar field, real scalars, phi, and then we cover complex scalars, phi and pi star. And now we're getting into the new objects, which are called sphere fields, and they're denoted with the psi, the quantum mechanical wave object, but it has nothing to do with wave. It is just another field that they're calling spinors. So what? Well, matter field fermions. Fermions are what we call particles moving on half. The easiest fermion that everyone really knows is the electron. And these particles arrive, like we call this as Peeling, right? So this is a Peeling particle. You may ask, okay, we're made of fermions, but there's a Peeling equation where how do they connect? Well, of course, when you quantize this equation, when you quantize the spinor field, you get 1/10 of the field, the happens to be particles moving on half, and these are what we call spinor or fermi. And everything is perfect so far, but there is trouble and paradox. The trouble is the position transformed down the Lorentz direction, like so. We have talked about it in the first lecture. So you have a Lorentz matrix, and to get to a new matrix, you just have to basically the vector transforms out of the Lorentz transformation by this product. Right? That's fine. But these spinors, so under this transformation, the scalar field will remain active. However, these spinors are not really so nice. They don't transform in a very nice manner under this change in position. So then you have psi that goes to a new psi, but then that new psi is generated by this complicated looking transformation. So this is not just a Lorentz transformation, but this is a more complicated one. So this is what we call the spinor representation of the Lorentz group. So this is not as simple as that. So that's why this equation is so much more elegant. It's not really easy to work. So we are getting into it. So building this transformation requires that you define an algebra. And this algebra is known as Differ algebra. And it's the algebra that relates more matrices, relates the Gamma-nu. They satisfy this Poisson bracket, which is commonly known as the anti-commutator. And they give you this relationship. So you have two quantities inside square curly braces. You basically multiply the two and add that. That's anti-commutator, or that's the boson product of classical. For the commutator, you do multiply them and subtract. So this is going to be important, this anti-commutation relationship. So it turns out that if you take the anti-commutator, the gamma mu and gamma nu anti-commutes to these two AW nus, where eta is a beta stimulus, right? And this one is the identity. So how many gammas do we have? We think 4, but it turned out we actually have 5. But let's start with the 4, because we have 4 space-time indices. So we have 4 matrices. Gamma 0, the 0 component gives you the gamma 0 matrix, which is the off-diagonal identity. So you have 0, 0 here, and on the off-diagonal we have 2 by 2 matrices. So you can see what this is really. It is a matrix inside you also have so the inception of matrices. So this is not just 0, 1, 1, 0. It is actually 0, 1, 0 matrix, 1 matrix, 0 matrix, 1. Okay. Similarly, for gamma I can go from 1, 2, and 3, the spatial coordinates. And these gamma i's are dependent on these sigmas. What are these sigmas? On the sigmas, those were initiated quantum again. Know that these are nothing but only sigma 1, sigma 2, and sigma 3. And these turn out to be important as well. Want to learn a bit much more about this Dirac equation. All this algebra and all of the matrices kind of coalesce to tell me that the spinor representation that I'm talking about here, the S operator, is given by this relationship, 1/4 commutator of gamma mu gamma mu. And you can find it out very easy, and you get this relationship. Okay, and using this spinor representation of the Lorentz spectrum, you use this to derive the Lorentz invariant Lagrangian that describes the fermions or spheroids, and then from there you use Euler-Lagrange equation to get to the Dirac equation. So we are taking it an inverted route because Dirac already has his equation. We don't need to get there. He has already given us this, but we want to understand how people. So basically, you have to develop all of this, connect the dots, and then develop a Lagrangian, which is saying. All right, cool. This one? This is to resolve this. Okay, good. Right. Now, we define something called the representation of the Lorentz groups. We define also something called the Lorentz group. We want to understand, like, these are technical terms, but what do they actually mean? So we know to break things down for you, right? So we want to know what a group is. Well, a group, to the bare minimum of the word, a group just means there's a set of elements. Let's call them G sub I. And there's a rule associated with these elements such that you multiply 2 elements of this set, you get a third element of this. That's basically a group. Okay. And of course, that's just one line definition of a group. But then this group, this multiplication is associated, there's some identity, the set will have some inverse and all of that. Those are group axiom. And I think Jimmy is lecture yesterday mentioned things about group axiom, right? So I don't know the more details, but this is just a one-line definition of our group space, which is going to be sufficient. So a group is basically a set of elements which you can multiply to get another element which is also in part of it. Okay. And then I want to know what a representation. Well, a representation is basically a particular embedding of these elements, GIs, into operators that act on a vector space. So you take elements from the group, and basically these are embedded here with just leaky that act on elements of. Okay, if you're talking about finite dimensional group or group representations, then these are the biggest matrices which act on vectors on some Hilbert space for us. For finite dimensional representation, these are going to be just matrices. GI is a representation of the group. GI without the ternary braces are just a representation of the groups. These are going to be just matrices. For example, for all groups, there is one representation that's a trivial representation, that's the identity representation. So every group can be represented by the identity matrix. Okay. Right. Now to find what we want to do is we want to get at the sphere representation. So you can't really just isolate one of them. You have to develop all of the representations for Lorentz group and track what to need. So to identify all of the representations for the Lorentz group, what you do is you investigate the infinitesimal transformation of itself. So basically how the group changes infinitesimal under infinitesimal changes its parameter. So this is going to be, this looks like a very complicated looking question. Maybe it is, maybe it is not. But essentially what this entails is how this x mu transforms under Lorentz transformation. So these theta that the Lorentz transformation angles and the betas are basically the boost factors, the gamma of them. So this is maybe complicated, but this is just temporary how you do have infinitesimal transformation. Okay, so you go from one x mu to a change in x mu via this operation. And these j's and k are what we call group generators in the four vector region. So what is the role of these group generators? Well, a generator is any element that can be expressed as follows. So you'd have an element of a group, let's call it delta, and these can be expressed as an exponential imperative of generator. So any element can be expressed in imperative of generator. So basically what we can say is the generators actually what's giving birth to the groups, and you can write every element in terms of the group generators. All right, and what do they do? Well, generators can be added and multiplied. So you can add them and multiply them, and the numbers that you can add and multiply, they form an algebra. Okay, for example, real numbers form an algebra because there is a rule for adding them, a rule for multiplying them. You can do both. You form an algebra of real numbers. However, the group elements, as I said, you can only multiply them. So group and generators are different in a sense that the group elements form a group. Generators form an algebra because they have sets of rules for both adding and multiplying. Group elements only multiply, so they form a group. And for now, the rotation form. There's a multiplication factor which you can rotate. You cannot. There is no rule for adding. All right. So a crucial group for us for quantum field theory and particle physics mostly is the Lie group. So it may spell lie, but yeah, you phonetically you say Lie. It's a Lie group, and there are many Lie groups. Important for us would be the Lorentz group. There's an example of a Lie group, and a Lorentz group has infinite number of elements, but crucially, it has finite number of generators. So how do we unpack that state? Well, in quantum field theory, you have infinite degrees of freedom. So basically, field spread over all space-time. However, we can look at one single point in space-time and identify a finite number of degrees of freedom for that. For example, we can zoom in on one point, and that one point can either go this way, that way, right? So you can identify at least a finite number of degrees of freedom for one particular point in space-time. So that's also good to know. So generators are finite, but the elements are. So with that example, you know already what J's and P's may be. J's and A are basically rotation there. So the generators of the Lie group form the Lie algebra. For the Lorentz group, these J and K will form an algebra. Okay. The multiplication rule for a group is for a Lie group is given by this Lie bracket. And you identify this Lie bracket as the commutator. Okay. So if you have two elements, two generators A and B, they give you the commutation relationship of AD minus BA. This is basically the Lie bracket. Okay. So you can kind of identify whether quantum mechanics is connected to group theory. But group theory gave you four quantum. So everything was built on group theory because it turned out that fundamentally particles are particles are described by these different Lie group. So therefore, Lie groups are critical in a sense that QED is described by 1, we call it 1. Weak force is described by SU2. Strong force is described by SU3. And so to develop a standard model of particle physics, you need to know what a Lie group is and what their role is. Particle physics. Okay. Oh yeah. Now, getting down to business of the spinor representation of the Lorentz group, we have first a Lie algebra. So remember, generators form an algebra, and the generators of the Lorentz group are J's and K's. So J's and K's will form an algebra. So the Ji, J sub J form an algebra that goes like this. J and K form an algebra that goes like this, where epsilons are let me see the answer. And K's and K's have a minus sign in their algebra. Okay, so these may look familiar to people who have done quantum mechanics. They turn out to be basically angular momentum relationship, right? So these are Lie algebra for the Lorentz group, and then these pull for all representations. So whatever representation you're talking about, these always pull. These are fundamental structures of the Lie algebra. So we want to find a very specific one. We want to find an irreducible representation of the Lorentz group because we want the most fundamental elements to be describing what we want to describe, spinors or whatnot. So we want to find the irreducible one, which cannot be broken down to further simplified options. All right. So we start by defining connected to the generator and operator Ji plus, and that is defined by 1/2 Ji plus IKS. So basically the summation of two generators that you used to define another operator. Okay. And correspondingly, there is an I here. So that means you can define an conjugate operator to Ji plus, which is JNI minus. So basically has minus in front. Yeah. So therefore, because these operators, there's a Lie algebra has I's in it. So essentially you're basically looking at a complex representation. And it turns out there are two complex representations corresponding to J equals 1/2. Why are we interested in 1/2? Because spinor fields are basically going to be seen 1/2. So we have two representations. One is 1/2 comma 0, and the other is 0 comma 1/2. So what does this mean? What do we mean? 1/2, 0, 0, 1/2. On the face of it doesn't need that's a representation of maybe two vectors or something. Basically writing a row making, right? But if you think about it, basically can describe an electron spin up, spin out. Right? So that's how that's selected. Now these electron vector spaces as 2J plus 1 and J is 1/2, so we have 2 degrees of freedom. So each of these representations will have 2 degrees freedom. So representation, because we are finite dimension, we're infinite dimension, we can identify the representation as being negative. So we end up with 2 by 2 matrices because of these 2 degrees of freedom thing, and they satisfy this algebra for the new operator, Ji plus and Ji minus. So Ji plus communication relationship or algebra, whatever you want to call it, is this one. Ji minus with a minus, either is this one, and Ji plus and minus will be 0. Okay. So basically, what this tells me, if you can somehow measure both of them, their order of measurement doesn't matter. However, these, whenever the epsilon 0, whenever two indices are the same. These are Ji and Ji, this is going to be 0. If Ji and Ji again, it's going to be 0. So on and so forth. Okay? But we know what these are. These are just polynomials because they follow exactly similar looking algebra. Then a sigma I over 2, sigma j over 2, they follow, you look at basically, and they follow exactly the same algebra. So what we're getting at is that these two representations are kind of connected to the polynomials, right? So this forms what we call the SO3 algebra, the special orthogonal tree group. And the polymatrices that exhibit anti-commutation relationships, and that's going to be super important. The anti-commutators for the polymatrix are given as follows. So these are just, now basically some housekeeping just to keep track of things where they go from. So these are technical details, but we need them to develop our theory. So this is the anti-commutator of two polymatrices, and they had commuted to delta ij, and delta I give a quantity. That's all. If I and j are different, that's going to be 0. That means these two anti-commuters. All right. And with all this new information, the Lorentz transformations for each representation then become, for 1/2 zero representation, you have j given by 1/2 sigma and a given by I over 2 sigma. Where do I get them from? A lot of different group operations, but we're not going to get that. But just take it for granted now that you get j 1/2 sigma and a to be I over 2 sigma. So crucially, you notice that j is the rotation part of the Lorentz transformation. A gives you the boost generator. Now the boost generator are imaginary. So then there's maybe some problem. 0 1/2 is given by j 1/2 sigma, fine, but the a's are the conjugate minus I over 2 sigma. So what's that can mean? Well, the j's are Hermitian, but the k's are anti-Hermitian. Hermitian, the corresponding adjoint and the operator are not the same, anti-Hermitian. Okay, so that's marks. So you want your operator to be Hermitian, so this is kind of problematic as well for spinor algebra. And elements on which the spin 1/2 representation acts. So where on these act on something, like for example, B must act on a vector C or something like that. The states they act on are basically called spinors. Okay. And the spinors that they act on, these are called psi r 0, 1, 2. This is the right-handed flying spinor. And psi L is 1/2 0, and that's the left-handed one. So for the right-handed wild spinner, you have the right side filled up by 1/2. With the left-handed one, you have the left side filled up by 1. So basically, you can remember that by. So right-handed, left-handed tree, sound later tree, mirror images differently. So that's where right-handed, left-handed comes in. There is a symmetry on a square symmetry, chirality related to it. But I'm not going to that. Maybe you talk about and. We see each. Oh yeah, of course. Like you can do that. I can't remember at this point, but yeah, you can always exponentiate, investigate the impact and facet. Okay, so but the trouble is there exists no finite dimensional unitary representation of the Lorentz groups, and unitarity is important because our operator that we want to basically want to build a Dilbert space with has to be unitary. So this is problematic because there exists no finite dimensional unitary representation of the Lorentz group. So that's going to be a problem. Now, so we need finite dimensional representation, right? And that leads to the fact that we are dealing with scalar fields. And scalar fields are, let's break it down into two components. So psi r is the right, but it can be decomposed into two components, psi 1 and psi 2. But why so? We already have two spinors. Why do you have to decompose into two psi x and psi y? You already have two pairs, psi r 0 1/2 and then psi l 1/2 0. But why do you break them down into these two component matrices? What can the two components really be? Any yes? Antiparacal, no, not for white spinners are under half. For white spinners, then basically it can be electron spin up position, spin down. Left rotation. The two components they meet. So then your psi L, you decompose them into two components. So we do that. And under infinitesimal Lorentz transformations, what we find is the size psi r changes with the thetas and veritas like this, and psi L stays with theta and veritas in the conjugate rotation. And this is what we call the spinor transformation. The spinners transform under infinitesimal Lorentz transformations following this. So you start with a spinner, you end up in the new spinner after you have gone through this multiplication. Now the job is to build a Lorentz invariant Lagrange. Basically, we want to give the Dirac Lagrange that we was the Dirac, but that everything you build has to be Lorentz invariant, right? Because we're working with space-time. Space-time represents space-time respects Lorentz invariance. So we build a Lorentz invariant Lagrange. We want to at least, and then that case we need to identify which terms are allowed and which terms are not allowed. So what does that mean? Terms that are allowed and not allowed. The allowed terms are going to be individually Lorentz invariant. You cannot ever have a term in the Lagrange which is violating Lorentz invariant. So you would always need terms in the Lagrange which are Lorentz invariant. So what does that mean? Lorentz invariant. Again, to recap, you have a Lorentz transformation initially. You put that term in. If it spits out of the same term, that term is good to go in the Lagrange. Right? It doesn't see Lorentz the invariant other nodes. Right? So the allowed terms turn out to be after you have gone through all of these derivatives, start with the dust has settled, and you have done your hard work, you find that the allowed terms are these looking terms: psi r data, partial of t, psi r. You have psi r data, works with j's, sigma j, sorry. You have psi l daggers, and you have psi r daggers, psi l. So these kind of products. So not all products, and we say you identify needing one thing. There is no term with three psi's or three products of psi data. There are always two. These are more bilinear, right? Because it turns out if you have three spinners in there, it's psi for right? So you don't really want. So these are terms that are allowed. Okay? And then we can build a Lagrangian, and it turns out the Lagrangian is this. We basically use the T minus UK and develop this Lagrangian for the spinor fields. And these spinor fields, we have defined them to be bias pairs. So we call this Lagrangian the bi Lagrangian. Okay. So this is the mass term, the mixing of the psi r's and psi l greater than psi r with the mass parameter. And these are the kinetic terms. Okay. So the psi r's has a sigma multiplied to it. The psi l's have a sigma bar. The sigma bar is basically the constant of all these. So it's basically a lot of terms, but remember, all of these terms is Lorentz invariant. That's important. You can forget about the Lagrange part out. Let's look at the important big picture. What are we building? Right? There's a lot of algebra that can go into, and you build this Lagrangian after a lot of work of 50 pages or whatnot. But the big picture should not be lost. You want to build a Dirac Lagrangian. If you haven't done so far, all the terms that we include into the Lagrangian must be Lorentz invariant. Okay? All right. Now, sigma mu's are one that's the identity and the sigma polymatrices. Sigma bar is then the polymatrices. Now, we want to make it cleaner because also we want to go towards the Dirac Lagrangian. So to make it cleaner, we introduce Dirac spinners. So we introduce spinners psi, but now psi are made up of psi l's and psi r's. But what are psi l's and psi r's? Psi l and psi r are just Y spinner, two component Y spinner. Then you're making up a component. You're making up a spinner which has one Y spinner here, one Y spinner here, right? So each Y spinner is two components. Then what is this spinner? How many components does it have? 4 components. So a core component spinner is what we call a Dirac spinner. A two component spinner is what we call a pi spinner. Okay? So that joint of this sigma bar is basically the row matrix, and these two are the Dirac spinners. Okay, or Dirac spinner and Dirac. adjoint spinner or whatever. All right, now what can these four components identify? Yep, we have biospinners, two components. We said, okay, one can be electron in spin up position, one can be electron in down position. But then we have now four components in a Dirac spinner. So what can they identify? Now you're on the right track because you have four components. One component can be electron spin up, one component can be electron spin down, the other two can be positron spin up and positron spin down. So in one spinner, you have a encoded particle and antiparticle, but we're not yet there. I mean, we know in Einstein that these are antiparticles, but Dirac can do it because that's late, right? But it's good to know that it's going somewhere. And we also define these other matrices, these gamma matrices that we used to define the Clifford algebra to be these matrices, all right? So these are big matrices. This is a 2x2 matrix itself. This is a 2x2 matrix itself. So this is a 2x2, this is a 2x. So this is like 4x4. Right? Gamma matrices. So we call them gamma matrices. We also call them Dirac matrices because they help us on the Dirac algebra. So essentially, where do they go? You identify sigmas and sigma bars, and you identify psi L's and psi R's in these terms. Basically, you can clean this up. You can encode all the psi R's and psi L's inside psi or psi bar, and you encode all the sigmas and sigma bars into these gamma matrices. Then you have a simplified little Lagrangian, which is the Dirac algebra. Isn't that absolutely beautiful? Look at this mess. Look at this one. Like absolutely bored of this. So this is the Dirac algebra. And from the Dirac algebra, it's one easy step to get to Dirac equations. Basically, solve for the Euler-Lagrange equation, you get what we have, the Dirac, the full plane equation function. Right? So this is where the Dirac equation actually came from. And the solutions to the Dirac equations are what interests us. You manipulate this in your own time, and you will find basically K waves, right? These are basically going to be very similar to what we have for our own. So these are going to be plane wave solutions, and plane wave solutions of two types. Because you have two types of spin, one psi, one psi bar. So you have this is only one equation for Dirac, but you also have the anatomic equation as well. So that we didn't write down, but you will have. So you have the plane wave solution. It looks like u e to the minus I p x, and dp e to the I p x. Okay, then minus I p dot x is I p dot x. These UPs are four component spinners. VPs are also four component spinners. So basically, this is psi, this is U. This side, this is B, but this is also four component. It's just, right? Writing it out a plane wave solution requires you to introduce two more spinners. And this is problematic because this, you can break it down very easily and it will give you positive energy solution, positive frequencies if you are thinking about it in terms of wave. But this one right here, give you the idea. That can give you negative frequency solution or negative energy solution. So this is what led Dirac puzzled for a long time. He was very puzzled about the existence of the negative energy solution. What do you? We know now, but we didn't know that. He didn't know. Right now, the next step is quantize the Dirac. So we know the Dirac equation. We know the spinner field. Now we want to quantize the Dirac equation. So we want to quantize the spinner field, and that will lead us to perm. That will lead us to spin. So let's do that. We start. Remember how we quantize the scalar tree? We elevated everything to operators, and then operators acted on compact space, and everything went from there. Then we introduce the creation and annihilation operator for the scalar field. We connect on phase standpoints and then generate particles and whatnot. We're going to start going that same route, right? So we proceed just as a scalar field by defining these variables, like it is a conjugate momenta, and then for the Lagrangian here, you just insert the Dirac algebra, and you find that it's just I psi bar. Yeah. So this is material is actually the center. This is related to making things variant invariant, but don't worry about that. And really, these are elevated to this and the Hamiltonian these are elevated to your operator, right? These are operators, and you promote also the psi daggers and psis to operators, and they satisfy these permutation relationships. So psi and psi y and psi dagger and psi dagger, they go to 0. But here we have new things to worry about. We have alphas and betas, alpha and betas. What are these things? Well, the space time is encoded in the x's and y, well, the space at least. But what are these alpha and beta? These are spinnering to keep track of which spinner you're talking about. Okay? Which drug spinner you're talking about, which drug component of the sphere you're talking about. So you're talking about the top component, the second component, the third, whatever. Okay? So these are spinner NVC. These are unique spinner. You don't have the scalar field. Yeah. Right. Okay. So then, if you do the permutation relationship of psi and psi dagger, you get this dilemma, right? So these are bookkeeping things. So the operators, what are they? Well, you want expressions for your operator, psi and psi dagger. So yeah, you basically solve these things and find out what you get. But essentially, the big picture is you get that sort of you get. So side x can be expressed in terms of these new things. Well, these are Lorentz invariant vectors. That's fine. And you have a new term that the sum s equals 1 and 2, because basically you have a two-dimensional representation. And this is the u's, and the b's are very, very fruitful. And s here is the speed index, and b tells you the moment, right? So momentum length. So if you compare it to the scalar field expression, these are the new things. Everything else, I know very single. Okay, so this is for psi. For psi dagger, you have similar looking thing, but then every undaggered one gets a dagger, every daggered one gets a. So that's all we. And now, well, you have described your expressed size and psi daggers in terms of BDs and C. But what are B's and C's? Well, you know what B's and C's are. They're going to be creation and annihilation operators. They will create what? They're going to create fermions. They're not going to create C. So from this, you have expressed size in terms of these C's and B's. So we want to express their permutation relationships in terms of the commutations of B's and C's. So we build that up. We find that B and B dagger and this permutation relationship is not really problematic anymore, because we know how to deal with this kind of operation from scalar fields. But this one here is not good. Why? Because if you compare the two, you see a relative minus sign. This minus sign, we don't like minus, we don't like negative energy. So this minus sign is going to be crucial, and that's going to be a stumbling block in our attempt to quantize the spinner field. Okay, so keep that minus sign in your head. So, right, so to summarize, these B daggers of NS will create particles corresponding to the USP getting spared. Okay, so these are basically solutions of the BRAC equation, and C daggers will be particles with this solution, ES. So remember what ES were actually? We were the ones that were giving you the negative energy or negative treatment. So ES will create negative energy things, BS dagger will create positive energy. You already know which one is problematic. So then you use this to build up the Hamiltonian. So we have psi and psi dagger. You know how they act and whatnot. So you express this Hamiltonian density, integrate over whatever, and you get a Hamiltonian. The Hamiltonian is looking okay so far if you don't really use those. So this one we have met before. This one we have met before. I mean, not exactly this one, but we met something like this when we quantize the Taylor field. Hamiltonian at this kind of a term. This led to interdivergences. and we knew how to deal with that. We just model order our operators and we just brush it under the rug. We don't care about it anymore. So this is fine. This is a green light. But then there's a red light. The red light is you have a C dagger and a C with a negative 10 up front starting from this combination relationship. But why is this a problem? Because this is fixed by normal order, no problem at all. But this is a disaster. And why is this a disaster? Well, this tells me really that Hamiltonian spectrum, that is the energy level, are unbounded below. So you can seemingly create from the ground state downward, because they have negative C, any amount of states you want. You can have -1, 2, -3, negative infinity. That's not really good. Basically, you're essentially having a power of infinite state in the negative direction. That's not a right. So that problem, and that's a disaster for Dirac's equation. But Dirac in his infinite wisdom knew how to solve it. And I forgot to animate it. Fermions, actually, we cannot go that route because we use communication relations or BRs and PRs, whatever. And we use commutation relationship for the spinor trees. But fermions, described by the spinor tree, they don't really obey commutation relationships. They follow anti-commutation relationships that go like this. So instead of the commutator of B and V dagger, we must use the anti-commutator. And instead of C and C dagger commutator, we use the anti-commutator. And you automatically see that the minus sign has gone away. Right? The minus sign, the problematic minus sign from the commutation relationship goes away. And following from this kind of setting, if you develop the Hamiltonian, you see, okay, this term was not a problematic term, seemingly now it's solved. It has a plus sign, right? But there's still a problem. If you work out the Dirac equation, you still get C daggers with acting on VP, a negative energy state. Now, this means still, even if you have a plus sign here, it means the Hamiltonian had no zero state. It's still unbounded below, right? You can get to the negative solution somehow, but it's still unbounded below. Nothing really physically it's stopping it from like building the cover state in the downward direction. That's not. Now, this is where Dirac's brilliance comes in. He assumes that, okay, what we physically measure are just complementary. What we physically measure are the ones that we actually see in the lab or the particle detectors, whatnot. These are positive energy states. But what about the negative energy state? How do we get rid of them? Well, he posits with new idea that the negative grounds to define a drama state. He basically said all these infinite down states can be all populated bilateral. All populated bilateral. He called them a sea of electrons, right? But that is problematic too. That would mean in the true vacuum of the universe, you have a negative cosmological constant. But of course we don't. Dirac didn't know that. His idea of this sea of electron can't work. Why? Because from that sea of electron, he say, okay, you can excite the ground state, right? You can excite the ground state. If you excite the ground state high, the electrons will escape from their trapped sea of electron. They will see it leaving behind what you call hole, right? These holes are positive energy. The electron trap is now empty of electrons. So there's a positive charge, electron, the negative charge goes away. The charge foundation works. But then we said, okay, but if they're excited, these holes are now cosmically charged particles. But then they're exactly similar to electron. Because hole is basically the creation of electrons leaving somewhere. So what are, well, he posits the positron, right? So positron with that, everything similar to exactly the same to the electron, but with the plus sign. So that's where antiparticles comes. This is in its infinite wisdom. He gave up antiparticles. 2 years down the line, they detected antiparticles. But the story is not done yet. Because Dirac equation only works for fermions. So it seems to predict only fermionic antiparticles. But you don't only have fermionic event particles. So that needed more development. All right. So the interesting phenomena structure, right? Now that we have developed the Skinner theory, like quantized Skinner theory, we know now how fermions come to existence by the excitations of the Skinner fields. Now, the interesting things happen when fermions and other particles meet. The spinors and scalars, they're not separate anymore. They can talk to one another, they interact, and they give us the good things. They give us up, right? So what we do is build up a Lagrange vector. So that's how we do it. First, write down the Lagrange. So you have a Lagrange unit that will include scalars and spinors. So first, let's start with the pre-scalar and pre-spinor. And this is the pre-scalar equation. You must have memorized by now. I've shown it so many times. And this is the Lagrangian form Dirac, right? This is a Dirac productive, but this is free, completely free. There is no interaction. Now, this is where psi is the spinor field. It's the playground of fermions, and phi is the scalar that we know. And gamma mu's we now know are gamma matrix. But this, on the face of it, is completely a boring kind of Lagrange. It's just a Lagrangian where you have a new piece added to it, just phi. But it doesn't do it. It's just pretty boring. It's pretty vanilla. So what do we do with it? Well, interesting things happen, as I said, when you make interaction, when you open the doors to communication. So the more useful Lagrangian will include interfield interaction. So you will have pre-scalar, pre-spinor, but then you have interactions that we call Yukawa interaction. The Yukawa interactions are of this form. When you have psi bar psi talking with the phi. So you see spinors interacting with K. So this is Yukawa interaction. He used this to, and G is the coupling law to the straight of the direction. Yukawa first proposed this kind of interaction when he was trying to explain the interaction between nucleons inside the nucleus. And he said that for the nucleus to stay stable, for the strong chords to be communicated, he predicted a particle that is now known as the pi meson, a pion that we have this kind of an interaction. So a pion, he said, he took it to be a scalar, and then that are basically interacting with the nucleons, which are fermionic field. Okay? So basically, this was supposed to be what Kukawa said, the mediator of strong force was supposed to be a pion, but we now know that's not the case, right? But this is also incredibly successful because this kind of an interaction is extremely strong. And in CAP, we know that this kind of interaction exists because everything that has mass must have this kind of interaction. This may be the Higgs field, this may be the electron and also interacting, and this gives you fermionic mass. Okay? Yeah. So the potential is related to this kind of a current. So this kind of a current we need to call as. All right. Now, we are getting to the end of the sector, and we finished last sector with a fermion. Fermion. I'm talking more about fermion. A Feynman diagram. And you're going to, towards the end of this lecture, we'll find that. But now, we describe Feynman diagrams with Hager. We'll describe now Feynman diagrams with Fermi. So that's where interest lies. So, first you assign some rules to code your Feynman diagram. So let's end up here so that I can see. So for every incoming fermion with full momentum E and speed R, you assign a spinor. Okay? And for each outgoing fermion, you assign you do bar spinor. Okay? This R label is basically the spin label. The speed label is the momentum label. So this is what a fermionic diagram looks like. This is basically how a Wiplow interaction may look like. It is essentially a fermion coming in to a vertex, or every fermion coming into a vertex at X switch this factor of U R P. Right? So then what about the other one? Well, for every outgoing fermion, you attach a bar P. The momentum arrows and this arrow on the line have nothing to do with each other. The momentum arrow just tells you if the fermion is coming in or if the fermion is going out of that vertex. The arrows on the line can tell you that your particles are in. So we see the arrows align with the momentum. We automatically know that these are describing parts coming out. Just electrons, either coming in or going out. Okay. Now, the second rule is for anti-fermion. So we look, Dirac has posited these anti-electrons-like things, positons. So we have rules for them as well. So for each incoming anti-fermion looks like this, which is kind of confusing, right? Because you have an arrow in the opposite direction on the line itself, but that just tells you this is an anti-particle one. But the momentum points the other way, the correct way. So the anti-fermion is actually moving this way in time and kind of go there. So for every incoming fermion, you attach a V bar, and for every outgoing anti-fermion, you attach a VR. Okay? And always look at the arrow. The momentum arrows have nothing to do with the lines in the arrows of lines. And then you have these vertex, get a factor of minus I lambda. Yep. That can be will be G. It's just a complete constant. And like each internal line in your diagram will have a propagator factor, because internal lines are basically propagators. And we have two kinds of propagators in the theory. You have either scalars, and scalars are technically labeled by these dashed lines. And you have maybe fermionic propagator. For the scalar propagator, we have I e square minus m square plus I at top. This was previously not there because that was a toy model. This is a real model. So I wanted to do this term here. You automatically know that there's some singularity building up on this denominator. For those who have taken complex variable, you know that this may blow up. Essentially, may not be very contoured equation. So this is final split, but that is separate out the holes by level so that if you read the holes, then you plot your own holes. Okay. So then you have fermionic propagators. These are internalized, which are solid, and they get a factor that goes like this. You have I, E plus M, but with a slash. So this sign rotation above. So when we talk about Dirac's Fermi and we developed this equation, we saw a gamma mu partial mu in the equation. So you have the gamma mu this partial mu by everywhere. Okay. You have gamma mu P u, gamma mu partial mu, gamma mu everything. Right? So one upstairs, one downstairs. We have these lines everywhere, all over. So if you want to write everything down, it will be a pretty big expression. So we want to condense our expressions down, and slash to P just means you have a gamma mu upstairs multiplying a P. So we have a dot product of a gamma. Okay, so that's the meaning of the slash. Okay, so the slash is not really a pi quantity; it just means a dot product, a scalar. And for the scalar, it's not really proper. And then you impose what we say momentum conservation. How do you impose momentum conservation? Well, really, you include delta function, right? Just like before. You define for each vertex a delta function, the momentum going in, added to momentum going out. So that causes energy momentum. And they integrate over the loop. So let's look at an example. And then, finally, importantly, we need to add an extra minus sign. So if you have multiple diagram, previously we had two diagrams and so forth. We added the two to get the total lap. But then if you have fermion in your theory, before you add the two, you have to look at, did you flip over any vertex? Did you flip over any interaction? You flip over fermionic interaction, you insert a minus sign in front of your plus sign because of spin statistic. Because switch fermion, you gain an extra minus sign. Switch boson, you don't carry mine. So add an extra minus. All right, now going to the example. We want to look at nucleon scattering, but nucleon with P first. So that this is the Hyman diagram that we can talk about. Really, the mediator. So fermion comes in, to interact via a scalar. Let's say pi liaison or something. Scalar, pi liaison is actually a skew scalar, but simplify things down. So maybe this is the Yukawa interaction of some sort. So two fermions come in and two leave. Okay. And we first label our momenta. External momenta gets two labels now. One for the spinor index S and one for the momentum index P. So this is PS, this is QR. Q is a momentum, I is another spin label. So one that's interacting with QR here, we're labeling in Q prime and labeling R prime. Here we're labeling this with ES and a P prime and S. So these arrows are the moment arrows. This tells me that this comes there. This tells me it goes up. And similarly for the other two. So that's our final diagram. We have no line, we have no arrows here because it's a scalar. It doesn't matter which way it goes. It will either exit a vertex and enter one, or it will enter a vertex exiting the other. Momentum observation is pretty obvious, the scalar. So we don't really need an arrow on the scalar line. All right. So now use the prescription for the Feynman rules. For every vertex, you have a minus I lambda factor. So we have two vertices here, minus I lambda squared. For every fermion line incoming, you get a factor of UP. So incoming is UPS and UQR. You get these two factors for these two incoming fermions. For two exiting fermions, you get factors of U bars and U bars, right? So we have two exiting fermions. You get U bar S prime, U bar R prime. Okay. And then you have to include momentum conservation and integrate over that propagator. The propagator is a scalar. For every scalar propagator, you have this factor, the propagating factor, the fermion the ion propagator, I over k square minus m square for the phi epsilon. The scaling is the internal moment. Okay. Right. Now we are left to conserve energy momentum. We include delta function. We need two vertices, so we need two delta functions. So one delta function, p minus q prime minus q, maybe here. So p comes in, p prime. Where is it? I think I messed up the label. So it's p minus q prime minus k, and the other one is p minus q prime plus k. So p comes in, p prime goes out, k comes in, right? The other one will be switched. Right. Now all you have left to do is integrate over that internal moment. You have only one integration because you have one propagated. You integrate over d4q. We get rid of one factor up to pi to the 4. We reduce an algebra. And what we end up with is the amplitude. But this is not the true story. This is not the full story yet. Because like we did before, you can switch with which P interacts. You can switch P to be interacting with Q prime. You can switch Q to be interacting with P prime. So you get another diagram like that. So this diagram, we have a new amplitude, but then if you add the two, that's completely correct. There will be a relative minus because here you're kind of switching which fermions are interacting. So we're basically switching this one with that one. So any switch of fermions lead to an extra minus sign because of Fermi statistic. So ultimately, if you add the two, what you end up with is this amplitude, and that is left for as a homework for you to solve. And you see the negative sign here. So I gave you the answer. You apply your Feynman rules to this diagram and see if you get it. Right? Okay. So I think I'll stop here. If you have questions, yeah. This is a little bit more technical. Maybe I lost a few last part. So to recap, we have covered scalars, we have covered fermions, we have quantized both theories. So we are now ready to go into the realm of standard. The standard model has interactions that we call QED, QCD, and then we form a group, a gauge group that kind of tries to merge all of them together. That is actually three processes to process one. All right. So we are going to start with QED briefly, and then QCD, and then we'll talk about the Higgs mechanism, and then how it connects into the Pascal model, and why is the standard model one. Hopefully by tomorrow, we'll have a little bit more knowledge than